We're now going to talk about the periodic table. We will use the periodic table all year, and it provides a wealth of information to us. It is truly the chemist's most important tool. It was developed by Russian chemist Dmitry Mendeleev, who started to see patterns in the types of elements. He started to arrange them not just in rows but in columns.
In 1869, a Russian chemistry professor named Dmitry Mendeleev was writing a textbook for his students when he began to wonder how he could best explain to them the 63 elements that were known at the time. To help formulate his thoughts, he constructed a card for each element. On each card, he wrote the name of the element, its atomic weight, its typical properties, and its similarities to other elements. He then laid the cards out like a game of solitaire and began arranging them over and over, searching for patterns. Then came the moment of discovery. Before him was something extraordinary. The elements fell into 7 vertical groupings. Each periodic grouping had members that resembled one another, both chemically and physically. Mendeleev had discovered the periodic table of the elements, a map showing how all the elements related to one another. A map so precise that Mendeleev believed he could also use it to predict the existence and properties of 3 elements no one had yet discovered. One would be like boron, he said, one like aluminum, and one like silicon. Eventually, the elements were discovered, and Mendeleev was proven right.
There was actually a little bit of controversy because a German chemist named Lothar Meyer had come up with roughly the same idea, but Meyer didn't quite have as much courage. So that's actually an interesting thing. Here's this German who comes up with the same idea of periodicity, of which there were hints already before, but he doesn't make the predictions that Mendeleev does. So here we see the power of a risky prediction in having people accept a theory. There is nothing more powerful than making a prediction that's not obvious.
And then have it come true.
And have it come true. The periodic table is our icon. I mean, that's what we associate with chemistry. You go into any chemistry room, you see it.
Why is the periodic table of elements significant? It forever changed the way that everyone would learn and understand the elements. The periodic table of elements is to chemistry as notes of music are to a Beethoven sonata. In honor of Mendeleev, his name is now literally attached to the periodic table. The element 101 was named after him. It's called Mendelevium.
So in the 1800s, Mendeleev would have stated the periodic law in a fashion such as this: when the elements are arranged in order of increasing mass, certain properties recur periodically. Well, that's not quite the periodic law that we state today. The difference is Mendeleev worked in terms of mass, but Henry Moseley, a British chemist who worked for Ernest Rutherford, he developed our modern periodic law, which associates the periodicity with atomic number, or the number of protons in the atom. And before we go on, I wanted to mention that Henry Moseley was such a highly contributing chemist while he was still in his 20s. He had so much promise, but he died young in his 20s in the Battle of Gallipoli. So this leads us to a periodic table of its modern form arranged according to the number of protons in the atom. Let's now talk about electrons. We say that proton count increases by 1 as we move from left to right across the table. What are the electrons doing? Well, electrons also increase by 1 as we go left to right across the table. But why do we have this step down to a new row? Here's row 1, here's row 2. There are 7 rows to the periodic table. This has to do with the idea of shells for the electrons. The protons are all being added into the nucleus, but the electrons are flying around exterior to the nucleus, and when we drop a row, we are expressing the fact that this next set of electrons have to exist further out from the nucleus than the lower rows. And so we call them shells. It's sort of like nested dolls, Russian nested dolls. But we see that the electrons always want to be close to the nucleus because the nucleus is positive and the electron's negative. And the preferred space is right there next to the nucleus. However, there's a capacity of 2, and then they are forced to exist further out. So 7 shells of electrons around the atom. And they're not just concentric spheres. They have all sorts of shapes, as we will learn. So when we talk about atom sizes, they do get bigger as you go down the table, but they get smaller as we move from left to right. So it makes sense that atoms get larger when we go down the table because we're adding more shells, which reduces effective nuclear charge, which we haven't defined yet. But atoms get smaller as we move left to right, and that doesn't necessarily make sense. Let's talk about that. What is effective nuclear charge? Effective nuclear charge is the number of protons in the atom minus the number of electrons in the lower shell. So if we look at sodium, we're saying Z effective, the effective nuclear charge is 11 minus 10, or 1. Here's sodium, element 11. It has 11 protons and 11 electrons, but 10 of those electrons are underneath. There's only 1 electron in the third shell. That 1 electron has a net pull of plus 1, 11 minus 10. If you look at the effective nuclear charge of aluminum, it has 13 protons minus the 10 underlying electrons for an effective nuclear charge of plus 3. Therefore, the outermost electrons have 3 times the pull towards the nucleus than they do for sodium, and aluminum is smaller than the sodium atom. Let's compare beryllium and oxygen. Beryllium has 4 protons and it has 4 electrons. How are those electrons distributed? Well, 2 of them are in a lower shell and help to cancel out the pluses from the nucleus. So we have a net plus 2 that the outer electrons experience. So beryllium has a plus 2 pull from the nucleus. Let's compare that to oxygen. Oxygen has 8 protons and 8 electrons. But of those 8 electrons, how many of them are underneath, negating the protons? They're the same 2. So, in effect, electrons on the outermost shell of oxygen have a plus 6 pull. 6 times the pull of a lithium, and 3 times, plus 6 versus plus 2, 3 times the pull of a beryllium. So, you see that as we go from left to right, the atoms shrink. Why? Because the net positive of the nucleus is building as we go from left to right from the viewpoint of an outermost electron. I will note, you see a little bump out here as we go from column 7 to column 8. That has to do with repulsion of the electrons as the outermost shell fills. The next trend we want to talk about is ion size. First of all, what is an ion? An ion is an atom that has gained or lost electrons. We say cations are the atoms that have lost electrons and they've become positive, and they are smaller as a result of losing something. Anions have gained electrons, and they are bigger than the original atom. There's something called the octet rule. It has to do with the perfection of 8 electrons in the outermost shell. It makes atoms stable. Well, metals are on the left side of the table, and they are very far from having the perfect 8. They lose electrons and become cations. And column 1 metals would only need to lose one outermost shell to go backwards to the octet, and they would establish a +1 charge. Column 2 metals would lose 2 electrons to reach perfection of the octet, so they would be +2 cations. On the opposite side of the table, you look at column 7, which has already 7 electrons in the outermost shell. If it could steal one more electron, that atom would reach the octet and become more stable. So in column 7, we see a -1. These become anions and are fulfilling the octet stabilization by adding an electron. And then on the far right, you have the noble gases, which are already complete with 8 outermost electrons, and they don't get involved in swapping electrons at all. The next trend I want to talk about is ionization energy. It's the amount of energy required to remove an electron. The noble gases on the far right have the highest ionization energies because they're very stable. The second ionization energy, to take the second electron away, is always larger than the first because we're building up more and more positive charge on the parent, and that's harder to pull it away. We see ionization trends such as this. Interestingly, the hardest to remove electrons are the ones that destroy the perfection of the octet that the noble gases enjoy. Okay, so we see it's easy to take away the electron on the first column elements because they can barely hold on to them. Their Z effective is +1. But on the far right, the noble gases have a +8 Z effective and can really hold on to their electrons. Next trend, electronegativity. This is a measure of the atom's ability to attract electrons. The number 1 most electronegative atom of all is fluorine. Fluorine is given the highest value of 4 for electronegativity, and everything else is compared to fluorine. This is work done by Linus Pauling at Caltech. It helps us predict polarity of molecules, plus minus balance. Electronegativity table, and we can see the most electronegative atoms are fluorine, oxygen, chlorine, and I include nitrogen in there. I always say FONCl. They're the 4 that have electronegativities above 3. All of the other atoms are below 3, and you'll see very low electronegativities over on the lower left. This says these atoms are not very good at pulling electrons towards themselves. However, on the right, up in column 7 especially, we see good attraction for electrons. And then in column 8, we really don't have these atoms participating too much in pulling electrons because they're already stable. Okay, so those are our major trends on the periodic table, and now I want to focus on the regions. We have a very easy quiz that you need to basically brute memorize these, and let's talk through these regions. There is a staircase on the periodic table that separates the metals from the nonmetals. The staircase, these metals are partly metal, partly nonmetal. These are called the metalloids. But everything to the left is a metal, which means they give away their electrons. Well, column 1 is called the alkali metals. Column 2 is called the alkaline earth metals. The red zone here are the transition metals. Under the stairs we have the post-transition metals. And then we have the rare earth metals, the lanthanide series and the actinide series. To the right of the stairs we have the nonmetals. One of the things that should profoundly stand out to you is that most elements are metals. There aren't that many nonmetals. They are up here in this triangle. There's also the halogens in column 7 and the noble gases in column 8. Those are the main periodic table trends I wanted to go over with you. There will be a quiz at the end of this unit in which you convey all of this information from this talk on a blank periodic table. Thanks for your attention.